Good morning. I'm in Arizona right now. We've had a little bit of bandwidth problems. We're having about 46 degrees C right now, so it's hopefully I'll leave my video off and hopefully it's good. We started looking at this benchmark just a few months ago, not very long. We got on it at the very end. So our goal was just really to look at what a open foam polyhedral mesh would look like on your benchmark geometry. We are in Berkeley. We're a very small company. We mainly have been working more in the aerospace and the automotive. However, we're the same team that did AutoCFD. For those of you with gray hair like myself will remember. When we started Ennova Technologies, this is basically what we sort of recognized was that the geometry is becoming very, very large. We've seen models of millions of CAD surfaces. More and more physics are being tackled, acoustics, CHT, radiation. And unlike in the past, people are very resistant to manually mesh, yet as everybody understands, you need a really good mesh to get a good CFD result. So the direction of Ennova is how do you sort of rationalize all that? How do you try to build a tool that can work towards those goals? So our approach, we're a client-server architecture. We want to generate the mesh on the same machine that the actual CFD solver is going to go on, so you don't have to be transporting large files across the network. Obviously, we're very parallel in nature. We wrote our own geometry kernel to handle the specific needs of geometry. We include CAD cleanup as part of the meshing process. It's all one single process as opposed to a separate CAD cleanup and then a mesh. Every time we do a CAD cleanup operation, we check whether we can mesh it. And we're trying to embed in the actual meshing the best meshing processes or knowledge that's around, like for example, proximity, curvature refinement, intersection avoidance, things that people would manually do, or normally we try to do as much as we can. Generally speaking, most people using Ennova are starting from the CAD geometry, not triangles, although both are treated the same. In this workshop, we use the topology mesher, and that's like generating a surface mesh from the actual CAD data itself, not the STL, and then growing prisms, building a volume Delaunay tetramesh or advancing front mesh on that, and then converting the whole thing to polyhedral in the end. And so what we were just trying to do was build a mesh that was a similar characteristics as your committee mesh and see what sort of results we got from that. And also, maybe what some of the disadvantages or advantages of using that type of mesh on the automotive. So probably can skip over that. I think I jumped ahead. So the polyhedral mesh, for those of you which are not quite sure haven't used one before, it's very easy. It's essentially taking the same, basically swapping the cell centers, taking the nodes in the mesh and just connecting them up a little differently. So basically, every time you have a triangle, you put a vertex in the center of the triangle, throw away the three vertices of the triangle, and then connect all the centers. And then you end up with a mesh that looks like a beehive mesh or a traditional polyhedral mesh. So some solvers actually do that in their stencil, I think, and some may do part of that. So sometimes the polyhedral mesh is not such an advantage for solvers, but I think in Open Foam's case, I think it's an advantage. So we just looked at the case 2A, and we started with a CAD mesh, and we looked at many, many meshes. I mean, I've generated a sequence of meshes from 5 million polyhedra all the way to about 65 million polyhedra. Today, the 52 million polyhedra is about approximately the same as your 157 committee mesh. There are differences. It's very difficult to get the sizing the same everywhere simply because of the different meshing technologies. But that's the a general rule of thumb is that if you have a 50 million polyhedra, that sort of corresponds to about a 6 times that, which would be a 300 million sort of general cell model. And then if you want to, and then basically if you have the same number of nodes in the mesh and you compare a hex core mesh with the polyhedra, you end up having 2 polyhedra cells for every hex core, like triangle. Imagine if you take a wedge element and cut it in half. So basically that's where the 50 million comes. So, approximately 150 million hex core is where we think it is. That was what the mesh looked like. We tried to do the refinements similar to what you have in the committee mesh, maybe a little coarse, not quite so many boxes. One of the big differences, of course, of doing the mesh this way is that you have a very gradual and gentle growth rate in every direction. We don't have the 2-to-1 transitions that the Octree approach has. So typically, because of that, often people are using the polyhedral approach and acoustics, things where you have waves. Maybe not so much in subsonic external error, but just typical the convergence result. And here's some of the results we've got. What you're seeing, the black is the experiment. The blue for this particular case was the CD for Ennova, and the green is your results from the committee mesh. What we were running is we ran open foam, just in the simple foam with Menta SST, as simple as we can, running on the assumption that if the mesh behaves well on the steady state, it's most likely going to behave better on some of the other more appropriate solvers. But we didn't have time to go back and look at any of the transient runs. So that's something that we probably will do in the future, but we haven't had time today to do that. I will, apologize if the graph is upside down. I'm from the aerospace side. We always plot minus CP, but that's the results that we got for the 52 million mesh against experimental data. And I think I got in the wake region. If anyone, how are we doing on time here? So what we were looking at was just a polyhedral mesh against your committee mesh. Obviously, we started very late, just I think it was May or even maybe April, May was when we started with the idea that we should participate in this conference. Some of the important things to note is that the meshing process is inherently batch, or so it lends itself to automation. The idea behind it is that we want to avoid putting the onus on the user for the skill level. One of the things we've seen on the aerospace side is that you have engineers, incredible knowledge from NASA on what makes a good mesh, and from what we've done on the aircraft side is that basically trying to embed that knowledge in the actual Ennova meshing process. And that's why we're very keen on learning as much as we can on the automotive to repeat what we've done in the aero for the automotive, so that, for example, like on a trailing edge of a wing on a plane, typically 16 to 17 grid points is required to capture the flow for a transonic flow. Stuff like that has been found out just empirically over the time. So any sort of knowledge about that, or how to treat the tires and how to combine prism layers, in those regions. We're trying to make sure Ennova can recognize that automatically and apply those without having to do any work. Typically on a mesh, a valid engineering mesh, the user only needs to apply like 4 or 5 numbers, max size, min size, curvature refinement, proximity at a global level, and then local level if they want to override Ennova as possible, but typically very few numbers to get a starting mesh. If anyone wants to take a look at the mesh or try running themselves, I'll like to make them available. As I said, if you don't want to have such a heavy mesh, you just want to try a smaller one, we've made some meshes down to about 5 million polyhedra. So I think, is that about my time?